This is quite an interesting pair of simultaneous equations to solve because they are just two equations, but yet we have actually four different unknowns: modulus of z, w conjugate, w, and z. And if I were to make w conjugate the subject and then trying to replace this, that means within one equation we will be having modulus of z, we will have w and z. So that is not something that I know I can solve. If I were to try to make z the subject and I replace this z that is within the modulus by w conjugate and w, we will potentially get quite a tedious equation to try to solve for w and w conjugate too. So one way that we can probably give it a try is to make use of the fact that modulus of z here is a real number, which means that if I were to be making w conjugate the subject, this will be modulus of z plus 3 plus square root of 2i. And modulus of z plus 3, let's try to make sure that we recognize this as a real number, because if I can recognize this as a real number, a purely real part of w conjugate, that means w will simply be modulus of z plus 3, the real portion, minus square root of 2i. Then if I were to see this as equation number 1, this as equation number 2, and this as equation number 3, if I were to sub 1 and 2 into 3, we will get one single equation with modulus of z and z, which isn't the most ideal, but I think we can still probably work on that. So let's give that a try. We will substitute equation number 1 and equation number 2 into equation number 3. So w conjugate, I will replace it by modulus of z plus 3 plus square root of 2i. And w here, we will replace it by modulus of z plus 3 minus square root of 2i, then plus 5z is equal to 1 plus 20i. And this can be cancelled. I will be left with this. So we will have a 2 times of modulus of z, 3 plus 3, this is 6. Moving over to the other side, we will have a 1 minus 6, it will be negative 5. So I have a plus 5z minus is equal to minus 5 plus 20i. And I think this is a right moment when we try to rearrange everything to the real plus I imaginary, and that will require me to replace z by its component. So I'm going to be letting z be equal to x plus iy, with the aim of rearranging the left hand side into the real plus I imaginary. So on the left hand side here, we will have a 2 of modulus of x plus iy, which is going to be square root of x squared plus y squared, then plus 5 times of z, which is going to be x plus iy also. Then this will be equal to minus 5 plus 20i. So for what we are looking at here, if I were to rearrange the left hand side into the real plus I imaginary, this is the real portion, so square root of x squared plus y squared, and plus 5x is also the real portion, part of the real portion. So this, I'm going to group it together. As for the imaginary portion, we have a 5y. And I guess this makes it very easy for us to solve for y, because if I were to match the real to the real, the imaginary to the imaginary, then we will be getting 5y to be equal to 20. So y here will be 20 divided by 5y is equal to 4. And we can then substitute it back into here to try to get an alternative and a value for x. So let's substitute y into this. It will be 2 square root of x squared plus y squared, so plus 4 squared plus 5x. This is going to be equal to minus 5. So let's try to solve algebraically for x. I'm going to bring this over to the right hand side. So I have a 2 square root of x squared plus 4 squared is equal to minus 5 minus 5x. Let's square both sides. So 2 will become 4. Then this will be x squared plus 4 squared. I should have let it be 16 from the very beginning. So this is equal to 16. Squaring this is going to be 25 plus 50x plus 25x squared. If I were to shift everything over to the right hand side, I will end up with a quadratic equation, 21x squared plus 50x minus 39. This is equal to 0. Solving for x, I'm going to be getting two values for x. X is equal to minus 3, or x is equal to 13 over 21, which means that I can get possibly two complex number that z is representing. And that will be z is equal to this, which is minus 3, y is 4, so minus 3 plus 4i. Or z can also be 13 over 21, then plus 4i. But if you were to look at the question asks us to find the value of z, which means that I'm expecting just one z instead of two z values. Let's try to verify which one is going to be correct. And I think what I'm going to do is to try to substitute the z back into here to see whether it satisfies this. If I were to substitute it back, it is actually satisfying this equation. But this, if I were to sub it into the left-hand side, it is not going to be equal to minus 5 plus 20i. So with this, I will want to reject this. So this is not applicable, because if I were to substitute this z into this, then 2 modulus of z plus 5z will not be equal to minus 5 plus 20i. So this gives us a reason for the rejection. So now we have rejected one value of z, which means that we can make use of this z and we substitute it back into w to get the value of w. So which w should we be using? Let's make use of this. So w, we already know z is equal to minus 3 plus 4i. So the corresponding w will be modulus of z, which is minus 3 plus 4i, then plus 3 minus square root of 2i. So this is going to be square root of 3 square plus 4 square, which is going to give us a 5, because we are doing a square root of 25. Then plus 3 minus square root of 2i. So 5 plus 3, this is equal to 8. 8 minus square root of 2i. For this equation here, we have one of the roots, that is 8i. So what we want to do is to apply the factor theorem to solve for a. Because if 8i is a root, and if I were to let fz represent this polynomial here, this is iz to the power of 3 plus 8 minus 2iz square plus az plus 40. And since 8i is a root, by applying the factor theorem, we know that the function where z is replaced by 8i, this is equal to 0. F of 8i, this is equal to 0, which means that it is going to be I of 8i to the power of 3 plus 8 minus 2i, then 8i to the power of 2, a times of 8i plus 40, this is equal to 0. Then I can make a the subject. A is going to be equal to this. Bring it over to the other side, we will have a minus I of 8i to the power of 3. Bring this over to the other side, we will have a minus of 8 minus 2i, then 8i square. This, bring it over to the other side, minus 40. This divided by 8i. And if we can just press this into the calculator, we will be able to get the value for a. And a is going to be equal to minus 16 plus 5i. From the previous part, we know that a is minus 16 plus 5i, which means that fz is going to be iz to the power of 3 plus 8 minus 2i z square plus a, which is now minus 16 plus 5i, then z plus 40. And we can re-express this. This is a cubic polynomial, and we have one of the roots, that means z minus away 8i. This is going to be one of the factor, and we are going to be having a quadratic factor over here. So for this quadratic factor, let me assume it to be a z square, then plus b z plus c. And I'm going to try to use comparison, comparing the coefficient of the left and right hand side to find a, b, and c. If we were to compare the z to the power of 3, the coefficient of z to the power of 3, on the left hand side we have I, on the right hand side is going to be 1 times a, which means that for the coefficient of z to the power of 3, we are looking at I to be equal to 1 times a. this tells me that a is just simply equal to I. And if I were to compare the term that is independent of z, this 40 over here, so the term that is independent of z on the left hand side is 40, and on the right hand side we will obtain it by taking minus 8i multiplied by c. This tells us that c is just going to be 40 divided by minus 8i. If I were to just press this in the calculator, this is 5i. As for b, I think I'm going to try to make use of the coefficient of z squared. So let's try coefficient of z squared. You can also definitely try for the coefficient of z. I think both should give you the same answers. So on the left hand side, I have 8 minus 2i. And on the right hand side, we want to extract out only the coefficient of z squared. So this times this is going to give me a z squared. So 1 times b. The coefficient is b. And this times this is going to give me z squared. A is I, so we are talking about plus minus 8i multiplied by a, which is I. So from here, we will be able to get the value for b. B is going to be equal to minus 2i. So now we have a, b, c, which means that for f, z, this is going to be expressed as z minus 8i. Then a is I, so I z square plus b is this, so b is minus 2i z. Then plus c, which is 5i. And I can see the possibility of actually factorizing out I. So we might as well try for that. So I of z minus 8i. Then this will be z squared minus 2z plus 5. And now if I were to try to equate fz to be 0, we will be able to solve for the other two roots by letting this to be equal to 0. The quadratic factor, we'll let it be equal to 0. So now if I were to let fz be equal to 0, this tells me that z must be equal to 8i, which is one of the roots. It is already given to us by the question. So the other two roots will be obtained by this z squared minus 2z plus 5 equal to 0. And z here will be negative 2, which is positive 2, plus or minus square root of this square minus 4ac. This divided by 2a. So if I were to simplify this, I will be getting 1 plus or minus 2i, which are going to be the other two roots of the equation, where this is equal to 0. We are supposed to deduce the number of real roots to this equation, so we are going to try to relate this back to the original equation. And what we can see is that z is probably going to be replaced by iz. So if I were to rewrite this, I'll let it continue to be equal to 40 plus 40, which is the same as this. Then I'm going to group this iz together, and plus minus 1. It is like I square. So I square and this can be combined. We will have iz, then square, then plus 8 minus 2i, which is good because this looks like this. And we will have I z to the power of 3. So we need to have I to the power of 3, but here is positive 1. So let's multiply this. Let's convert this 1, the coefficient 1, to I to the power of 4. Which is going to be I, then I to the power of 3, which can be combined with this to give me iz to the power of 3. So now we can confirm that all the z here is going to be replaced by iz, which means that from the answers here, from the roots here, we know iz is going to be equal to 8i, or iz will be 1 plus or minus 2i. So for this, the root z will be 1 plus or minus 2i divided by I, which will be some kind of complex numbers. As for this, z is just simply going to be equal to 8. So we are expecting one real root for this equation.